So very soon we will start to talk about techniques that solve precisely this problem of taking a training sample as input and returning a function p as its output. But the first question to ask really is, why on earth would we want to do this? At first sight, this seems like a rather strange problem to be considering. But actually there's very strong motivation for considering it. So there are two reasons I'll give for considering the language modeling problem. The first is that language models are actually useful in a very wide range of applications. So speech recognition was really the first application of language models, and language models are critical to modern speech recognizers. Other examples are optical character recognition, handwriting recognition. Another example we'll see later in the course is machine translation. So in short, language models are actually useful in many applications. I'll come back to this point in more detail in a second. But the other reason for studying language models is that the estimation techniques that we develop later in this lecture will be very useful for other problems in NLP. So, for example, we'll see problems such as part-of-speech tagging and natural language parsing and machine translation, where the estimation techniques described are applied very directly. So let me go back to this first issue and describe in a little more detail how language models are relevant to the problem of speech recognition. And this will be a fairly high-level sketch, but hopefully you'll get the basic idea. So the basic problem in speech recognition is as follows. As input, we have some acoustic recording. So this is actually somebody speaking. On one axis, we have time. On the other axis, we have the amplitude or energy. And in a speech recognizer, we typically go through some pre-processing steps, something like the following. We would typically split this sequence into relatively short time periods. These are often called frames. Each frame might be, for example, around 10 milliseconds long. And then for each frame, we might perform some kind of Fourier analysis where we get energies at different frequencies within that frame. So the details aren't too important, but this is the kind of pre-processing we might carry out. Having performed this pre-processing, the task is then to map this acoustic input to the words which were actually spoken. So let's say, for the sake of example, recognize speech is what was actually spoken in this case. So speech recognizer takes an acoustic sequence as input and outputs a sentence or a sequence of words as its output. Now, in practice, there are often many possible alternative sentences which could have been spoken, which are quite confusable. So another example sentence might be, rec a nice beach. This is a famous example from the speech processing community. And the issue here is that these two sentences are quite similar from an acoustic point of view. And if you simply look at a measure of how compatible this sentence is with this acoustics versus this sentence, it's quite possible you might confuse these two sentences. And this is just one example sentence. In practice, there are many, many, many other possibilities which might have a reasonable degree of fit with the acoustic input and might be quite confusable with the true sentence, recognized speech in this case. Now, if we have a language model, we can actually evaluate a probability P of each of these sentences. And a language model adds some very useful information to this whole process, which is the fact that this sentence, recognized speech, is probably more probable than the sentence recognized beach. So the language model is going to provide us additional information in terms of the likelihood or probability of different sentences in the language. And again, there are going to be many others down here with some of them which might look acoustically like a very good match to the input, but which are completely unlikely as sentences in English. So in practice, modern speech recognizers use two sources of information. Firstly, they have some way of evaluating how well each of these sentences match the input from an acoustic point of view. But secondly, they also have a language model which gives you essentially a prior probability over the different sentences in the language and can be very useful in getting rid of these kind of confusions. Okay, finally, let's talk about a kind of very naive method for language modeling, just to get us off the ground as a thought experiment. So say we have n training sentences, maybe a few million sentences from the New York Times, for example. And for any sentence x1 up to xn, I'll just define c of x1 through xn to be the number of times that that sentence is seen in our training sample. Okay? A very simple estimate is then the following, where we define p to be simply c over n. Okay, so we simply count the number of times the sentence has been seen and divide by the total number of sentences seen in our training corpus. And this is a language model. You can verify that p is always greater than or equal to 0. And also, if you sum over all sentences, p will sum to 1. It's a perfectly well-formed language model. But it has some very, very clear deficiencies. Most importantly, it will assign probability 0 to any sentence not seen in our training sample. And we know that we're continuously seeing new sentences in a language, so this model really has no ability to generalize to new sentences. So the most important question in this lecture is essentially, how can we build models that improve upon this naive estimate, and in particular models which generalize well to new test sentences?